Hello and welcome to the final part of my Code It Yourself Worms series. This is going to be a little bit different to how I usually do the videos because I've got the last part of this video is a full battle royale of the worms fighting each other, and this video is really going to be about the AI strategy that I've developed to get them to do that. Now fundamentally I've not changed very much from the previous video in this series. I've added a prettier looking sky, and I've added a countdown timer and a health bar, and there are teams of worms, but I'm not going to go into very much detail like I usually would about how all of that's done. Instead we're going to focus on the AI. The Code It Yourself Worms game has now become quite a large project. In fact, there's about 1,000 lines of code. But please believe me when I say most of the code you've seen in the previous two videos. I've not made any changes to the create map function, I've not made any changes to the Perlin noise function, I've not made any changes to the boom function, and I've made one slight change to the cPhysics object class, which is the inclusion of this damage function, which we'll see later. I've also made no changes to the camera tracking or the firing weapon routines, and I've made absolutely no changes at all to the physics engine. So let's have a quick look at the cTeam class, and this class is really just a wrapper for a vector of worm objects, and this vector is called vec_members. And there are two functions this class provides, and one is team alive, which just iterates through all of the members in the vector and checks to see if their health is greater than 0. If any of the worms have a health that is greater than 0, then the team is still alive. It's still available to take part in combat. And the second function is getNextMember, which returns a pointer to a cworm object. And this function goes through the vector one by one and wraps around. So this way we can work out which worm's turn it is given a particular team. And of course we don't want it to choose worms which aren't healthy. And you might be thinking, well, if a worm dies, why is it still a member of the team? Well, the object still exists. What I've decided to do is draw it as a gravestone instead of a worm. And if we look in the draw function of the cworm object, we can see is playable. This flag is directly set by the health of the worm, so if it's greater than 0, the worm is playable. Then we draw the worm using the draw partial sprite routine, as we did in the previous video. We also take this opportunity to draw the health bar underneath, which is just scrolling through the health values, setting pixels beneath the worm. We use the draw partial sprite routine because the single sprite asset that this game uses contains all 4 team colours individually drawn, and it also contains 4 tombstones with the team colours marked on them. So if the worm isn't playable, instead of drawing the worm sprite, we draw the tombstone sprite. So a team is just a collection of worms. Let's tick that off. Now the previous video looked at using state machines to govern the order of play, and we're still doing that here. The only difference is the allocate units has now been filled in. Previously it was blank. And it's in this state that we can set the number of teams or the number of worms per team that we want, and we can play with these numbers as long as we don't have more than 4 teams. And the first thing that we do is work out how much space does each team and worm need, because we want the teams to be deployed in a team, but the worms we don't want them all to be on top of each other, we want to deploy them next to each other in their teams. So once we've calculated the spacing, we create a team object, and then we add worms to it at the appropriate location. And we can see here where we're taking the vector of teams, we're taking the vector of members for that team, and we're pushing the worm to the back of that vector. So it's really just 2 nested for loops creating all the teams and worms. And it's quite nice. So for example, if I chose to have 2 teams but 10 worms per team, we could easily do that and see what it looks like. And there we are. 2 big teams. You may notice I've added the ability to zoom in and zoom out when the user presses the tab key. This was quite useful so you could see the overall state of play. Let me just put it back to 4 teams of 4. So I'm going to continue with my strategy of closing up the things that we don't need to see. The start play state is where the action happens, and it will remain in this state until one of 2 things has happened. The player has fired their weapon, which we saw in the previous video, or the turn time has expired. So in the onUserUpdate function now, I'm decreasing the turn time from 15 seconds just by subtracting felapse time from it. And in fact, we can see that here. The other major change to the state machine is the camera mode state. This state was responsible for controlling the camera following the object of interest, and it did so until the physics engine settled and then returned back to start play. But we're also now waiting for the physics engine to settle and then choosing the next object of interest. So if we've got teams of worms, it goes between one team, then to the next, and then it goes to the next worm within that team, etc., etc. So once the physics engine is stable, we can assume the action has stopped and it's time to choose the next team and worm to play. So to do this, I just increment the current team counter, and I make sure that that wraps around the number of teams that are playing, so we're always going between 0 and the maximum number of teams minus 1. But I'm also making sure that when I increase the team counter, that that current team is alive. Do they actually have the ability to play? If they don't, it just goes around and increments again. And it will keep doing this. Now, this leaves us with a situation where the next team to play could be the same as the current team that is playing. And in this case, that means there must only be that one team left. Therefore, that team has won. So we look for that specifically. If current team is equal to old team, then we go into the game over state. However, we want one of the teams to be controlled by the player and all of the teams to be controlled by the AI. And I've designated that team 0 is the player team. They're the red ones. So if the current team is the player team, we enable player control and we disable computer control, as opposed to the AI team where we disable the player control and enable the computer control. Once we've selected a new worm object to follow, we set it as the object under control and we tell the camera to track it. We reset the turn time back to 15. And I've set here the zoom out flag to be false, because that will make it sure that the camera zooms in on the worm that is currently under control, and we go back to the start play state. Let's just briefly look at how the zoom out function works. If we're not zoomed out, then we draw as we did in video 2. The only difference here is I've made the sky a gradient instead of just a fixed cyan colour. And as before, the objects draw themselves and draw across her to indicate in which direction they are aiming. However, if we have zoomed out, then we rescale the sampling points for the map, and we draw the whole map on the single screen. Again, I need code to draw the gradiented sky. And the objects go and draw themselves. But we can't just get them to draw themselves natively. We have to do some clever offsetting to get them to draw them in the right location, because remember now we're looking at the whole map on the screen. And we also need to indicate that we want them to be drawn at a smaller scale. So I've modified the draw function to include a flag, which we set to true for when we're in zoomed out mode. If we just briefly look at the draw function for the missile object, it uses the draw wireframe model function as it did before, but if the zoomed out flag is set to true, then it fixes the scaling factor to 0.5 instead of the radius which was set before. So drawing the landscape, we can check that off too. At the top of the screen, I'm drawing health bars that represent the total health of the team. And I'm calculating this in a very trivial way. I'm just iterating through all of the team members and accumulating their health. And I use the fill function to draw a coloured rectangle in the team colours, the appropriate length across the screen. The countdown timer in the corner was a 7-segment display, and this code, believe it or not, generates that 7-segment display for us. And you might be thinking, what is that? Well, on the Discord server, we've had lots of little challenges where we tried to do some code golf, and this was the minimal amount of code required to draw a 7-segment display using the console game engine. I've decided to leave it in its golf form because, well, it looks cool and it's a little intellectual curiosity for any of those that do look at the source code for this project. So with all that out of the way, we can now focus on the real content of this video, which is the artificial intelligence, or AI. I decided early on that the AI shouldn't be allowed to cheat, so I'm going to restrict the AI to using the same controls that the player can use. And there weren't that many, so there was aim left, aim right, jump, and fire. And if you remember, you hold down fire to energize the weapon, and when you release it, it takes the energy level and applies that as a velocity. And because I've restricted the AI to using just the controls that the player can use, this means I don't have to make any changes to the physics engine or any other part of the game. All I need to do is send the control signals to the engine that already exists. And just like we controlled the game with a state machine, I'm going to create another state machine just for controlling the AI. My AI state machine consists of 6 states, and we're going to start in this one, which is the choose strategy state. In this state, the worm is going to decide where it should walk to, and it basically rolls a dice to choose between one of 3 options. Option 1 is to walk away from teammates. Option 2 is to walk towards the middle of the map. And option 3 is to just do nothing at all. If the worm chooses option 1, this is quite a defensive strategy because it tries to resist having clumps of worms together, so when a missile hits, it's only likely to damage one worm rather than a whole cluster of the same team. Option 2 is quite an aggressive strategy because being in the middle of the map gives you the advantage of being able to hit most of the targets elsewhere on the map, but it does mean you're more exposed to being hit by other worms. And option 3, do nothing, means the worm just sits where it is and simply takes aim and fires. Depending on which strategy is selected, we can choose a location which is the target for the AI to walk to, which leads directly into our next state, which is our walk state. When we're in the walk state, we'll continue walking until we have reached that target position, or we'll stay in that state to carry on walking. And making the worms walk is quite easy, because they can only jump. So all we'll need to do is set a jumping angle based on the direction we want the worm to walk in, so it'll either be positive or negative, and we set our jump flag to true. Once the worm is in its new location, its next state is to choose a target. And my strategy for choosing a target is simply going to be choose a team which is not yours, and choose the worm with the most health on that team. Now, of course, we're going to have to examine the mathematics of how the trajectory and the projectile stuff works, and I'll do that just after we've finished looking at this state machine. But one of the byproducts of that mathematics is whether it is possible for the worm to hit its target, and if it isn't, the worm needs to move towards its target, which means we need to go into a second walk state, which, just like the previous walk state, has the option of staying in that state until it satisfies a criteria, and that criteria is that it is in position sufficient enough to hit the target. And as before, to walk, we simply set the angle to be positive or negative, and we set the jump flag to true. Once the worm is in a position where it knows it can hit its target, the next two states are really just animation states that make it look good for the player. So the first is aim. The worm has to move its cursor to the correct angle in order to hit its target. And in a similar way to walk, there are two exits to this state. One is target angle is correct, and while it's not correct, it can sit in its own state, adjusting the cursor for that worm, using the aim left and aim right flags. Once it's lined up the cursor with the angle that it needs in order to hit the target, it then enters the fire state. And just as we did with aim, there are two ways to exit this state. Firstly, the target energy required is met, or the state loops back on itself, issuing the fire flag. Once the worm has fired its weapon, it has finished. The game will move into the camera mode state, and eventually a new worm will be chosen. So we want to make sure that the AI goes back into its choose strategy state. But what I'd like to emphasize here is that at no point does the AI do anything that the player can't do. It only uses the same set of commands: jump, aim, and fire. So how do we determine the angle that the AI worm should aim for in order to hit a target? Well, let's make an assumption that the worm under control exists at 0, 0 in a 2D plane, and the target worm exists somewhere relative to 0, 0 within that plane. This gives us a change in elevation and a change in range. I'm going to draw a line between these 2 points. We know in our physics simulation that all of the projectiles will follow a parabolic trajectory. And what we want to find is the angle that we should aim the cursor in order for the projectile to follow that trajectory and hit that point. This is actually quite complex, and there are two unknowns. One is the angle, and the second is the muzzle velocity, i.e. what velocity do we fire the projectile at. And to make this simpler, the AI will always fire its projectile at a fixed velocity. Whilst looking through the maths for this project, I discovered this excellent Wikipedia page, which is projectile motion. And about halfway down the page, there is an interesting article, angle theta required to hit coordinate xy, and this is precisely what we're looking for, and it gives us this really nice formula. But rather curiously, it doesn't say how this formula is derived. But the formula contains all of the relevant parts that we need. We've got v, which is our muzzle velocity, how fast is the projectile fired. We've got g, which is gravity in this case, that's a constant set in our physics engine. And we've got x and y, which is the target offset location here, x and y. But I don't like just using a formula without knowing where it comes from. And when I look at this formula, I see a lot of similarities to the quadratic equation formula. Which hopefully you remember from high school. Now, in previous videos I would have happily derived this for you, but I did actually find this a little tricky. After a little bit of searching, I found this excellent video presented by Physics EH, where he steps through the derivation line by line. I've included a link to this in the notes below, but lo and behold, it turns out to be a quadratic equation. Fancy that. So rather than me just reinventing the wheel, I thoroughly recommend you go and have a look at that video. It's excellent. He's a very enthusiastic guy. He describes it wonderfully well. It's better than I could do it. And so go take a look. And so this equation uses only values that we know and generates the result that we want, but it also has one interesting byproduct which we can use to position the worms. And that is, we want to make sure that this remains real, i.e. it doesn't become an imaginary number when it's all calculated. And we can do that by making sure that the highlighted part here is always positive. So if we test that this is positive first, and it is, then we know that there is a sensible solution for theta. However, if this is not positive, then the worm isn't close enough. There is no known solution. There is no theta which a projectile could be fired at that will hit the target worm. So we'll move the worm forwards, towards the target. And so our walk towards target state is constantly re-evaluating whether calculating theta is possible. And if it isn't, the worm keeps walking towards the target. As soon as it becomes possible, it can then move on to the aim state. So let's have a look at the code for the state machine for the AI. My first state is assess environment, or choose strategy. And in this case, it just chooses a random number between 0 and 2. However, it's in this state that you could probably have the most fun about giving intelligence to your worms. Mine is quite crude. And the play defensive option is perhaps the most sophisticated, in that it creates a field of influence that decides what the worm should do next. But of course, these states could be governed by other outside influences, such as how much health has the worm got. You know, if it's low health, then it should play defensive. It also doesn't study the environment in any particular way. It doesn't look to see, well, there's an obstacle I can't pass, or there are too many worms in one cluster, nor does it try to work out where the best place to position the worm is for future actions. So this could be subject to a lot of further improvement. So if the action is chosen to be 0, play defensive, it works out which worm of its own team is closest to it, and walks away from it. The second action is the aggressive strategy. It walks towards the middle of the map. And the third action is don't do anything at all. Just stay where you are. So all of these actions will give me an safe position variable, which is a target location. I clamp this variable to make sure the worms don't deliberately walk off the map. And once I've chosen the safe position, I then move on to the next state, which is to move. Move is done by jumping. And providing that the worm isn't in its safe position, it needs to jump towards it. So depending on the relationship between the safe position and the current position of the worm, I choose a shooting angle and I press the jump key for the AI player. I also make sure that the game has to be stable before I can issue the jump key, or else the worms will simply fly up the screen. The player has this limitation too. Once the worm, here denoted as origin, has reached the safe position, or the turn time has gone below 8 seconds left, we then move on to the next state, which is choosing target. When we're choosing a target, we're not issuing any controls, so we'll set the jump thing to false. As mentioned earlier, my strategy for choosing a target is quite dumb. It just chooses a random team and chooses the healthiest member for that team. Again, more thought could be put into this, and the target need not necessarily be a worm. We could, for example, create a field of enemy worms and decide where is the centroid of that field, so perhaps we can inflict the most damage to several worms at once. Once a target worm has been selected, we record the target X and Y coordinates for that worm, and then we go and start calculating maths, which is the position for target state. This highlighted line is the equation that we saw earlier inside the square root. So we know that if A is less than 0, then the target is out of range. And so if the target is out of range, we want it to walk again. So it's exactly the same process as before. The worm jumps. We set the shooting angle, we wait for it to be stable, and we issue the jump flag. And we stay in the current state that we're in. I've included here an extra clause which is turn time, so the worm will only try and walk towards its target providing there are 5 seconds left on the clock. And the reason for this is the worm may routinely get stuck on the scenery, in which case it's got little option but to either blast its way through the scenery or blow itself up. Well, I prefer the former. It's going to have a go at trying to clear the scenery, so it simply fires in the direction that it's trying to jump. After all, with only 5 seconds left on the clock, it's probably not got enough time to line up the cursor and aim properly at a target. If, however, the worm is within range of its target, we can then carry on with the rest of the calculation to calculate theta, the shooting angle. Because of the plus and minus component of this equation, of course we get two solutions. One of the solutions always fires the projectile with the maximum height to reach the target, and the other solution fires the projectile with the minimum height to reach the target. For my implementation of worms, I do calculate them both, but I'm always going to use the maximum height, and this way the bombs will drop in from above. This has a greater chance of success than simply firing through the scenery. You may remember that the actual target energy required to fire the weapon, i.e. how much do we charge the bar up to, is fixed, and I fixed the AI to 3/4 of that of what the player can do, because the player can fire a little bit further than the AI. The AI is very good, remember. If it's within range, it will probably always hit the target. So out of this state, we end up with target energy and target angle. And then it moves on to the next state, which is aim. This state is really just cosmetic. It moves the cursor around with the same restriction that the player would have. And so it issues the aim right or aim left commands until the two angles line up, i.e. the worm's cursor angle and the target angle. And because it's floating point maths, this may never happen, so we have a clause here which says, well, if they're close enough, we fire. And the nice thing is, we could tune this value to replicate enemy difficulty. So right now, it's quite a tight tolerance, so the worms will be quite precise. But we could make this a little bit noisy, which would make the worms miss a little bit more. Regardless, once the shooting angle and the target angle are aligned, we move on to the next state, which is fire. And in this current implementation, the fire state seems a little superfluous because our energize is always a fixed amount. It's always going to be 0.75. However, it's nice to show the player the animation of the energy bar charging up. And so this state simply holds down the energize key until the energy level has reached the target level. And all of this information that we're using so far is completely available to the physics engine and to the control engine, and we'll see that in a minute. I.e., we've not had to change any other part of the game in order to accommodate the AI. Once the AI has discharged its weapon, it moves back into the assess environment state, waiting for the next worm to control. This leaves us with one last set of changes to look at, and that is how do we get the AI to actually control the worm. In the previous video, we interrogated the keyboard buffer to see which keys had been pressed, and this would represent the player input. Well, if we now govern this by whether the player is allowed to input, then we can selectively enable and disable player input control. The flip side to this, of course, is we can have enable computer control and the equivalent AI flag. So if either of these conditions is true, then it performs the action associated with that condition. Either the player is in control or the AI is in control. Regardless of who is in control, the action is the same. And this is unchanged from the previous video. In this case, this is jump, this is aim right, this is aim left, and this is to start charging up the weapon. So the only changes I've made here is adding this extra level of control to enable who is really in charge of controlling the simulation. And that is that. This brings us to the end of the big project for 2017, Code It Yourself Worms. All of the source is available on GitHub, of course, and I'd like you to download it and play with it and perhaps improve upon the AI, and it would be great if you could submit some videos of it working. The rest of this video is going to be a full battle royale between 4 teams of 4 worms, completely AI controlled. But if you're not interested in seeing that, I'd like to say if you've enjoyed this series, please give me a thumbs up. Have a think about subscribing. I'm going to take a little break now until the middle of January, so I'll see you next year. And so now it's time for one final battle royale to show it all coming together. The worms have entered the map, and it's the red team to start, which happens to be the player controlled team. I'm going to launch a missile somewhere across the map, and from this point on it is the AI playing the AI for all teams. So we can see blue have taken a shot at pink here. Fires pink high up into the air. Pink seems to be on the aggressive strategy now. It's moving towards the middle of the map. Takes a shot and hits 2 blues. Pink and blue are even at the moment. Green, I think, is taking a defensive strategy here. It's moving away from its teammates. But with pinpoint accuracy, also takes on blue. Not much love for blue right now. Red moving towards the centre of the field. Takes a good shot at blue, doesn't do that much damage though. Blue deciding to move away from red there. Probably for the best. But he's left himself in an awkward position. He's right next to his teammate, and that was a wasted shot. Let's see what pink is going to do now. Pink looks like it's going for green. Aiming backwards. And it's a direct hit on green. So red so far are completely undamaged. Green struggling to get out of the hill there, but it got there in the end. Takes a big long shot. They're just picking on the blues, aren't they? This red member has decided not to do anything other than take a shot, and it did so with beautiful accuracy. Oh, blue struggling to get out of the crater. Oh, it just manages it. Thought it was going to run out of time, but no, it got away with it. And it was a miss from blue. Pink on the offensive now. And that's another member of the blue team eliminated. Green again struggling to get out of these craters, but now it's a big target, green. If anybody aims for them, they could do a lot of damage to the whole team. But they are quite far away. I think red's moving in for the kill now. And it's an up and down shot to take out blue. And that's it, the blue team are eliminated. Right, pink has got a problem because it's basically stuck in a hole. So what's its strategy going to be? Going to have a quick go at some of the greens. And ooh, lots of damage to green there. That's always the risk when you clump your worms together. Green trying to move into position. I think this is a shot to nothing, but we'll see. Yep, not going anywhere. Red now moving in. These downhill slopes are definitely favouring the red team. And it's a lovely shot on the pinks there. Another pink worm gone. Now pink, very stupidly, has thrown another worm down into the hole. I think it's going to have little choice but to blast its way out. There we go. And green's doing a very risky up and down. Could have took itself out there, but nope. A nice shot on the pink. Brings the pink back into play in the middle of the map. Looks like a safety strategy from the red team. And tried to take out a whole cluster of worms there. And that's the first damage the red team has taken. It's storming into the lead. Almost lost the pinks there. We did lose a red at the same time. And that's it, the pink team are out, so it's red versus green. Green's got little choice but to move a bit closer now so it can hit the worms. I think this will be a shot to nothing. Now red's got quite some obstacles to overcome here. Doesn't need to get over the wall, and it looks like it's a... oh no, it's a miss, it's fallen short. Green is thinking about it, not quite sure. Nope, it's just going to fire and hope. Ooh, we almost did it as well. Red just a little bit scared by that, going to be a little defensive now. But now it's got a problem. It's dug itself in. Yep, blew itself up. Stupid red worm. Green unsure of what to do here. I think it's just going to have to blast its way out. And it blasted its way out of life too. Red moving in. Takes aim, but I think we're too far away. Yeah, they're going to have to move a bit closer. Green's got the right idea. Navigates the obstacle with ease. Takes aim. Oh, and it's a good hit on that red worm. Look at that, red overcame that obstacle with no problem at all. But now I think this one might prove a bit challenging for it. but it's a good hit. Right, now the reluctant green worm coming in for the kill. And this looks like to be a very direct hit on the red there. It was, and green have just taken the lead. This is back up now for the red team. Going to support his allies. I think this is a shot to nothing, but it does smooth the map out a little bit, makes it easier to navigate. Green did, well, it just blew itself up there. Stupid green. They've relinquished their lead now with silly decisions like that. Red clearing the obstacles that are getting in the way of them hitting green successfully. Oh, this looks like a good shot. And it is. And there's gravestones blowing all over the map. Green moving back in now. I think they've decided they're just a little too far away to do anything useful. And it's getting quite a tense 2-on-2 battle here. But there is a risk, the worms may take themselves out. You don't want to be hitting your own teams. Now the greens are a big target now for the reds if they can fire that far. But that's another red taken out. It was a good hit by the green, so this could be it for the red team. However, can the red team do 2 worms in 1 hit? We'll find out. And it did! Look at that! The red team take the lead. And to celebrate, we drop bombs all over the map.